Hi, we're M6 and today we're going to show you how our team of engineers develop materials for use in an aluminum mountain bike frame. Today, we will show you the material selection and finishing treatment processes that are undergone when designing a low to mid-tier mass-producible mountain bike frame. A mountain bike is a product where a careful moderation of factors must coincide to yield the best performance while ensuring longevity. While similar in appearance to other bicycles, mountain bikes are designed for off-road cycling. Whether bouncing through rocky mountain terrain or precariously navigating through breaks and dense vegetation, these bikes must be designed to repeatedly sustain impact without compromising their structural integrity. In addition, when pedaling up steep inclines, it is desirable to have a stiff frame in order to maximize the efficiency of power transfer from pedal to wheel. They're also designed to be as light as possible to make it easy to maneuver through coarse terrain and to maximize acceleration. Currently, steel, aluminum, carbon fiber, and titanium are the materials of choice for mountain bikes. Carbon fiber and titanium are quite expensive and generally reserved for high-performance bikes. Steel, on the other hand, has been falling out of favor for the lighter aluminum, but still remains favorable when high strength and low cost are the primary factors. For the aluminum frame we shall be designing today, our goal is to select a material that is easy and cheap to manufacture and process while still meeting strength, durability, and stiffness requirements, all with the intent of minimizing the mass of the frame. In order to do this, we have developed a list of design requirements that will serve as a basis upon which we will undertake our material selection process. Firstly, the primary function of our mountain bike frame is to hold the bike components together in a rigid manner under the load of the rider. Then, the constraints that we have can be split up into hard and soft constraints. The hard constraints, which must be met under any cost, are the material must be an aluminum alloy, it must withstand an impact load of 3,000 newtons, and it must survive 10 million fatigue cycles under this impact load. The soft constraints are, the mass should be less than 6 kilograms, it should have a high stiffness with a total deflection less than 3 millimeters, and the material cost for the entire bike frame should be less than $25 US. The objectives of our design are to minimize the mass, minimize the cost, maximize the resistance to corrosion while also maximizing the ease of manufacturing. The free variables are that the frame tubing radius, the type of aluminum used, and the finish process. From these requirements, material performance indices were developed. Based on the objective of minimizing mass with the radiuses and frame members being the primary free variable, it was determined that the following material property ratios were to be maximized. Firstly, the square root of yield strength to density. Second, the cube root of Young's modulus to density. And lastly, the square root of yield strength to the cost multiplied by the density, with cost being in cost per mass.
The filter for the different alloys of aluminum was based on the manufacturability. Only materials with moderately good or excellent cold forming, press forming, and weldability were considered. This is because to manufacture the complex geometry of the bike frame, it must go through these procedures. The next filter was based on the first MPI. Yield strength was considered to be the most important factor because the bike frame shouldn't deform under any circumstances as they are really expensive and hard to fix. Next, the remaining materials were plotted on the Young's modulus of elasticity versus density. The final MPI taken into account was the yield strength versus density. The final filter used for the available materials was to retain only those materials which exhibited little to no susceptibility to stress corrosion cracking. Aluminum 6061 stands out due to its simple manufacturing process. This has been proven because many bike frames have been made out of this material. Additionally, it's easily heat treated to improve strength and hardness. Like many other aluminums, it is corrosion resistant, and this makes it an easy selection over many other materials.
Aluminum 6061 T6 is a really common alloy that is mass-produced for a variety of different uses. It is 95% aluminum and consists of other elements such as magnesium, silicon, chromium, and copper. It has a Young's modulus of 70 GPa, yield strength of 280 MPa, and fatigue strength of 131 MPa after 10 million cycles. These mechanical properties make it an extremely versatile alloy for bike frames and are even used for making airplane wings. To manufacture aluminum 6061 and achieve a T6 designation, it must go through many steps to pass quality and safety standards. The aluminum can either be extruded or hydroformed to create the separate tubes for the bike frame. Extrusion is better for mass-producing frames as it is more efficient. Hydroforming is capable for more complex geometry and curves for bike frames that require it. These tubes must be welded together to create the structure of the bike frame. Any 4000 series aluminum alloy can be used as filler as it can be heat treated after it is welded. By welding the tubes together, it creates stress concentrations in the heat affected zones, reducing the strength of the aluminum in those areas due to the high heat of welding. The first step in the age hardening process is solid solution treatment at 530 degrees Celsius for 1 hour. This gets rid of any impurities and dislocations and creates a uniform solid solution. By increasing to the upper temperature region below the liquidus point, it allows us to ensure that the material is entirely in its primary phase, without much time spent heating it. At 530 degrees Celsius, 1 hour should be sufficient to be confident that it is indeed in a purely primary phase solid solution. The second step is quenching it down to room temperature with water. Quenching it with water is a quick and effective way to ensure that it is in a metastable, supersaturated solid solution state, meaning that it is almost entirely in its primary phase despite being at a temperature that would normally yield both primary and secondary phases. The final step is age hardening the aluminum at 177 degrees Celsius for 4 hours. 177 degrees Celsius is near the upper portion of the alpha plus beta region in the phase diagram. This decreases the aging time while still ensuring that the beta phase formation is thermodynamically favorable. Increasing the temperature too much, however, would result in a lower optimal aging time, reducing the uniformity of the beta phase nucleation. It can be seen in the hardness versus aging time curve for aging at 175 degrees Celsius that 4 hours is indeed the peak time for aging to maximize material hardness. Based on our requirements, for corrosion resistance, the aluminum can be anodized, but for aesthetic purposes, it is better to apply powder coating for finishing the final frame. The first step in powder coating is to sandblast the frame, which removes any oxides, oil, dirt, and grease from the frame itself. Then the bike frame is grounded, so when the electrostatic gun sprays positively charged powder onto it, the difference causes the powder to stick to the frame. Then, the powder is cured at 200 degrees Celsius for 10 minutes for a more uniform finish. This process takes relatively 45 minutes from start to finish.
After selecting a material, we chose to simulate the effects of a maximum loading case on the frame. Many assumptions were made when looking at the impact case of the frame, which included a completely rigid suspension and factoring down the maximum loading case to make analysis easier and quicker. This way we could take a frame and look at where its greatest stress concentrations would form. Using the analysis, we could conclude that it would be able to conform to our constraints such as 3000 Newton impact and being able to withstand this load for 10 to the 7 cycles. The major stress concentration showed up around the head tube, seat tube, and bottom bracket. However, the maximum stress that was experienced was seen in the rear triangle. The red area represents the highest stress concentration and can be read as approximately 82 MPa, which is under the fatigue stress of 121 to 130 MPa. This gives us confidence in the frame's integrity under maximum loading while still maintaining a safety margin. Another key aspect to improve the performance of the frame is to increase the stiffness and responsiveness of the bike. This can be proven by the maximum deflection experience on the bike frame under maximum loading. As seen in the diagram, there's a 0.7mm deflection on the head tube, which is under our constraints.
Ultimately, the material we chose for our mountain bike frame was 6061 aluminum with T6 age hardening. The reason for this is it meets all of our design requirements, having a low mass and low cost, while still retaining very high ease of manufacturing and high resistance to corrosion. As shown in our analysis, it meets all the safety and performance constraints that were set up by us in the beginning, while still being cheap and effective.